That's what I mean, I'm assuming it's like that.
All right.
It can't be like longer than
I think we're live. Going live.
Yeah.
All right. Dark up here. All right. So the homework keys are posted. Check them out. I wouldn't print them because they're long. I'm sure when you knitted, like when you use that weight table function, it does like all 100.
Oh wow.
Or whatever. There's ways to only report like the top 10 rows or so, which is probably what we should do, but yeah, don't print it. As part of the output, I did make figures. I did produce some figures that could be acceptable based on the simplest model. I didn't necessarily do like a full write-up. I didn't do a full write-up with everything. At this point, you should know what you have to include for, your test statistic, p-values, your conclusion. But what I did do is, as I was working through the problem, model simplification and post hoc tests, I was adding commentary on like what I was doing and why I was doing it. So there was a spot where I think we had 5 or 6 variables on one of our first problems. And when you check the assumptions, all of our assumptions are met, right? All of our assumptions were met. So what we could do is we can use GL multi and let AIC pick the best models for us. And then once we narrow down the model, if it's something simple, let's say main effects only, our assumptions are met. It doesn't change the fact that our assumptions are still met, which means we don't have to go through the trouble of restricted permutational ANOVA as post hoc tests. Our assumptions are met. Just use 2Ps or do ANOVA. All right, take advantage of it. The only time we really pursue those randomization tests is if we violated our assumptions. All right. Likewise, if you had a violation of assumption of, let's say, unequal variances, right, and your GL multi, the AIC selection, comes up with just main effects only, all right, you can use one-way analysis of variance. You might have to kind of trick it. All right? I wouldn't necessarily do it, but you can kind of trick it by taking residuals and then running the analysis on the residuals. Kind of what we see in some of the scripts, like what I did with the restricted permutational stuff. But pay attention to the homework. I kind of explained what I was doing and why I was doing it. You'll see when you use classical tests, when you use the ANOVA tables, it's just tedious. Updating the model, checking the ANOVA table. Updating the model, checking the ANOVA table. And it's very easy to make a mistake by not changing what the updated model is called. So one way I like doing is just adding a number, mod 1, mod 2, mod 3, and keep reminding myself that I'm updating that model until I get to the simplest model, and then mod simp is whatever that final model is. So check it out. I did run into problems. I'm sure you ran into it too. If you try GVLMA to check your assumptions, if GVLMA fails, you can't include it in your chunk. The knit will fail. So you'll see, what I did was add a pound sign in front of that GVLMA function, because that R will ignore that line. And I added another comment that said this failed, so I had to use graphical methods or whatever. So check it out. Definitely look at it. Look at it sooner rather than later. All right. Our exams are coming up. Right. I had the application part of the exam. I mean, it is finding simplest model, analyzing, interpreting the results. Right. I was going to have it go live on Friday, and then it kind of dawned on me that, man, Blake's getting hosed because he's moving this weekend, right? And then I also thought, well, why? If it's done, why not let it go live? So it goes live tomorrow morning. You can work on it the rest of the week. I did put the due date on Wednesday at the start of class. So that way, if you have issues with knitting, we can do it. Or we can kind of help you get it fixed, get it knitted. I did that instead of Monday because Monday is the graduate symposium, right? How many people are going to be gone? Oh, just 2? Oh, you guys missed it. Yeah, I mean, if we're going to have half, I was just going to say let's not even do class for that. How many people are going to that thing?
I'm gonna go watch it.
Yeah, you should all go and support. All right, you should all go and support because it's 4 to 5:15, right, and then the award ceremony after. So what we're gonna do is we just won't have class. Go support 2 graduate students who are presenting. Go look. What's that?
Where's it at?
Yeah, C.J. Davidson Center, I think.
Oh.
Usually where it is. Yeah, so go support, go talk to, look at other grad departments, look at their projects. You know, it's one of those. I have heard from other faculty that it seemed that our department tends to do good posters, good papers. So go check it out and support it. And that's why the test will be due on Wednesday, so that way we don't have to come here and try to fix it. That being said, the theoretical part will be open up on Monday. You can take it Monday or Tuesday. And really, so the theoretical or the application part is out of 60 points. The Blackboard questions might be out of maybe 15 points, 20 points. I mean, when you think about what we're doing, a lot of it was just learning the process and repeatability. So it'll be like, why do we do this? You know, what if this happens? What is our option? May give you some output in R and say, okay, what's your interpretation? Something like that. So it's not going to be terribly long. Maybe 30-minute time limit. I haven't made it yet, so be ready. All right. Any questions? Coming down to it. All right. So continuous variables. This is leading up to having continuous variables as an independent variable in one of these big regression models. All right. So before we get there, we have this possibility where we have a data set like we do, core.csv, that has numerous continuous variables, length, weight, volume of food. And one of our questions is, are these variables correlated with each other? Well, we can do that by using the core function. Now, if we give a data frame to the core function, it will calculate a correlation or try to calculate a correlation between every single column. All right, so go ahead and do that. Just read in your core.csv. I called mine core.data. All right, just type in core and your core.data and see what happens. So what did it do? What did it do? Okay. You have a table of what?
Correlation.
It is correlation coefficients. And it's a triangular table. Triangular table. Correlation, length with itself is 1, weight with itself is 1, and so forth. And then you have the upper part, and the is identical to the lower part. So the correlation between length and weight is 0.9717. Length and weight 0.9717. So if you're reporting a table of correlations, you really only need to report either the upper diagonal or the lower diagonal. You don't need to report all of this. But this is a quick and dirty way to look at all of this stuff. So if I have these data and I'm looking to include it as part of one of our regression models, one of the assumptions is that our variables are not correlated with each other. I see right here, length and weight, we probably are going to have a problem. Volume also probably have a problem. If we look at food, that doesn't look like we have a huge problem at all. All right, now what is huge? What's this? Minor problem? It's all relative. It's all relative to what we're doing, what we're trying to investigate. Generally speaking, anything that's greater than 0.8, it has a pretty high correlation. But some people would say highly correlated. All right. If it's between 0.6 and 8, it is moderately correlated. If it's 0.4 and 0.6, it's considered correlated. If it's below 0.4, we're kind of at, well, it's weakly correlated. And different fields, I think psychology and sociology have really kind of broken it down, or at least defined those terms. Less so in biology. I'd say if we're 0.8 or higher, we're going to probably have a problem. If we're like 0.6, 0.7, be careful. Be careful with that. And this applies no matter what type of method we use, right? So we can use Kendall's talk, core data. All right, we can generate it all at once, which is really nice. But what happens, I mean, this is like a really small data set. What more than likely happens is that you're going to have columns that describe when you sampled, where you sampled. Maybe you're going to have categorical variables in there. So how do we go about only producing the tables, or these correlation tables from the continuous variables? Well, this is where the subscripts come into play. We can reference our data frame and then use the brackets and specify what columns we really want to report. All right, now the format is the brackets, square brackets, comma, and then a list or a vector of numbers referring to the columns in your data set. All right, so why do we have a comma here? Well, this subscript is basically rows and columns. Well, we want all rows to be included, so we just leave it blank. And then the comma says, okay, what's coming next is the list of columns. So let's say, and we're going to demonstrate this, we have that's your head, core.data. All right, I'm doing the head because I want to see what the table is looking like. All right, so I can see I have 4 columns. The numbering goes 1, 2, 3, and 4. It goes right in order. So let's say we only want to do length and weight. How do we do this using the core, or using subscript? Well, it's core.data, square brackets. We want all the rows, so I just go ahead and type in the comma, and then I'm going to do C for a vector, and I'm going to say I want 1, 2. And we'll do method equals, try spear. All right, and that gives us the correlation of columns 1 to 2. Now we can also write it as 1 to 2, 1:2, because R will expand it. Whoops. 2. No parentheses. We could do it as 1 to 2. If we want the first 3 columns, we could do 1 to 3. We don't have to, the only time we need to use the C for concatenate is if we're going to put together a list. So let's say we want columns 1 and 2 and column 4. We can specify we want the length, the weight, and the food column. just by putting together a vector of the columns that we want to use in our correlations. You'll see that this produces the length, weight, and food. Pretty useful. Pretty useful if you're trying to do some other types of analyses. Maybe doing a ordination plot with some of your morphometrics. You got your entire data set, you want to make a distance matrix only from only your measurements. You specify which columns to make. So instead of trying to do subsets of your data set, just say, hey, I want distance matrix from these columns. All right? So we can use this to look at correlations of our continuous variables. Yep.
I haven't gotten mine to run for whatever reason.
Okay. Does it give an error?
Yeah, unexpected bracket, but I don't necessarily understand what.
Oh, you got a comment after there. Here it is. So it's your data frame and then a bracket. It's kind of like when we use data frame $sign. As soon as it has a brackets after the data frame, it's telling R, okay, pull out these rows and these columns. All right. So this works for generating the correlations, but it doesn't work for doing the statistical tests, for doing core dot tests. For core dot tests, you actually have to tell it which two variables you want to test for correlations. All right. Let me look. Nope. Now there are ways to pass it to write a function that kind of does it for each pairwise comparison. And I believe there's some packages that will also do it, that also have kind of done that, but we're not going to do it. All right, so these correlations represent raw correlations between it. And that assumes that none of the other variables that are in your data set depend on the other ones. So we know that that's not necessarily true, because if we have lengths and weights, those probably are used together to calculate a volume. All right? So a correlation between volume and length is giving us the raw correlation. All right? That could be useful. But if we're really interested in breaking down the actual correlation, the contribution of one variable's variance to the other variable's variance, so covariance type stuff. What we really would probably want to look at is something called a partial correlation. The partial correlation describes the interaction between multiple variables after we remove the effect of everything else that's there. So this Venn diagram kind of summarizes it. All right, if we're looking at the correlation between yellow and blue. All right, we're looking at this area here. The Pearsons, the Spearmans, the Kendall's-Taw correlation from like a core table gives us this entire shaded region. But that includes this effect too, so the correlation with the red variable. If we're really only interested in the correlation between blue and yellow, we want to get this shaded region and exclude this part. That's what a partial correlation is. So the partial correlation between blue and yellow is this region. The partial correlation between blue and red is this region. Partial correlation between yellow and red is this region. All right, it's the areas where only those variables overlap. All right? When is it useful? Well, it's useful when we typically draw these flow diagrams that show the association between variables. All right, this could be like a structural equation model that kind of came up. It's used in different fields. Sometimes biology uses it. All right, but the idea is we can use our correlations and compare them to the partial correlations to make interpretations about our data. So if our regular correlation between x and y is the same value as a partial correlation of x and y, then we know that no other variable is influencing our correlation. No other variable is having an effect on that association that we observe. If our correlation is greater than the partial correlation, now we know that we've got something else that's happening. There's other factors that might be influencing our observed association. So that's what these are. All right, so perhaps you have something called a mediator variable. Our interest is in this correlation between A and B. Maybe it's not a direct cause and effect, but our relationship between A and B is going to be determined by the effective variable C. Here we've got a regular correlation. After we remove the effect of C, it's entirely possible that our partial correlation is 0. Because these two are not correlated in any way. The only reason they appear to be correlated is because of the effect of C on each of them. Because each of these are directly affected by C. And they're affected by it in the same way. So, good example, and I tend to mention this, is a research paper that was published in California that said that watching TV causes autism. All right? Do you remember that, Cody? You remember that example?
Oh, in undergrad.
Yep. All right, undergrad ecology. It's a good example of causation does not prove correlation. So the idea is that
we use the pirate ship, the pirates.
yeah, we use that one too. Yeah, we use that one too. But anyways, with the autism and TV watching, what they did was they measured average daily rainfall, the number of days that have rained. And they assumed that if it's raining on those days, then kids are not playing outside, they must be inside watching TV. So then they went down and looked at autism diagnosis rates in those areas that correlate TV watching or number of rainy days and rates and said, well, if they're correlated, then there must be a cause-effect relationship. But if you do like a partial correlation with that, you're going to probably remove that effect because it's not, you don't have one acting through the other one. You've got this other aspect. Maybe, you know, in those areas that get more rain, there's more chemical pollution or something like that. All right? So regular and partial interactions tell us that. Other ones are like this. Where, again, we're looking at A and B. So A and B, now here, A directly or is positively correlated with B. A has a positive effect on B. All right? Let's say length and weight. Length directly affects weight. All right? But length also has an effect on what you're feeding on. All right? So if you look at your raw correlations between A and B and compare it to the partial correlation is actually going to be smaller because we're removing this pathway of our analysis. We're removing the effect of food choice. So perhaps larger fish are feeding on, you know, higher protein content, higher fat content, allowing our fish to put on more weight. Well, once you account for that, you end up with a much smaller partial correlation to account for that. You also have this situation where you do see the correlation, but A is correlated through B because A is positively correlated to C, or C is positively correlated to B. You take that out, now you end up with another partial correlation, 0 type of situation. So that would be a mediator variable. Our relationships, our correlations, are being mediated by some second variable. That could be a cause-effect relationship or could be another, let's say, correlation itself. If we have this situation where our partial is actually higher than our actual correlation, then we could have something called a suppressor variable. These are, I'm going to say, interesting. They're hard to explain, but they're kind of interesting. Probably a good situation that I've set up is this one, where A has a positive effect on C, but as C gets larger, it causes B to decline. All right? So when we look at the actual correlation between A and B, maybe it's 0, maybe there is no effect. But when we do the partial correlation, we actually see something. We see some relationship because we've removed this guy's effect. Who knows? This, I think the suppressor variable is an uncommon event, but it's something that you should be aware of. Now, are we going to get into this and doing partial correlations? No, we're not. We're not, but this is something that you could use it as. All right? We're interested in, let's say, overall clutch size of birds. All right? And you go out and you study and you record temperatures during the breeding season, during the nesting season. You measure food supply, or you estimate food supply. You have body size of the parents. You look at parasite loads, and then you have this other variable that didn't really get kind of a latent variable, maybe host genetics. All right. How do you go about analyzing all of these and making sense? Well, one way is to use structural equation models, which starts to give or generate these partial correlations between each of the individual variables, with the effect then that we can say, okay, this is how temperature affects clutch size. It affects it through both body size and food supply, which then affects our parasite load and ultimately our clutch size. How we get our total effect is to follow each of these paths to quantify or put numbers to that cause-effect relationship. In some cases, it's probably just going to be correlation because, again, we're not manipulating any of these things per se. So if you get into something like this, I'd like to say you're on your own, but R has a structural equation modeling package. There's several websites that kind of help walking you through all of that. And that is something that if we had like some other stats course, maybe we could delve into it and learn how to do these types of analyses. All right. All right, so are we going to calculate partial correlations? Nope, but know that R could do it. What should we know? Know what the definition of a partial correlation is and how you might utilize it and compare it to a raw correlation to make interpretations about our data. All right. Why do I present it? Yeah, basically for completeness. You may encounter this. You may encounter this in research articles. May encounter it other times, and we're going to see something similar when we do the regression analysis. All right. Any questions? No. Let's move on.
Pirates and global warming.
It is. Pirates and global warming.
Pirates about global warming. The decrease of pirates.
Yeah. So bring back the pirates.
Bring back the pirates.
Bring back the pirates.
Doesn't everyone just know that shit?
Classic. I don't know how that paper on autism ever got published.
That was published.
What was it
That
published?
wasn't like a.
Was it like in
That
a
was
medical
real?
journal?
I mean, there's,
I thought that was a joke.
They're not necessarily even watching TV on rainy days.
What's that?
They're not necessarily even watching TV on rainy days. That's
But it made headlines. I mean, that was a news release. Watching TV causes autism.
That's scary.
All right.
Is there data we have to download for this?
I don't know.
Yeah, it's not on like your data.
What?
Yeah. I was wondering.
Oh no. We introduced cabbages first. That's part of it. We're gonna work with cabbages. Kind of go through that.
Okay.
So that's part of it. All right. So what are we doing? We learned we're gonna have the test on categorical independent variables. All right. We're doing that. Now we need to include those continuous variables because everyone knows that you're gonna probably have continuous variables at some point. Soil moisture. All right. Average daily rainfall. All right. Average temperatures. All right. Height. Cover height. You know, with the pole. What's the pole? The site pole. What's that?
Robo.
Is that it? That camera you used? Matt's not here.
Robo.
Yeah. You actually have measurements. All right. How do we incorporate them in our analysis? All right. So our setup's still going to be we have one dependent variable. We're trying to see what the effect is of all of these variables on that one dependent variable. And then we're going to have anywhere from 0 or more factor level independent variables to 0 or more continuous variables, but in this case, we're going to start adding a continuous variable. All right, now this continuous variable can be one of two types. One, we may be interested in the effect of that variable on our dependent variable. The other one is we have that continuous variable because we think it's a covariate of our dependent variable. And we can remove that effect of the covariate to really see, do we actually have an effect? All right, how we analyze them, the difference between a covariate and actual independent variable or a predictor variable, there's no difference. All right, we're still going to kind of go through the same steps. The one exception is if we think it's a covariate, then we're probably going to need to leave it in the model, even though that term might be non-significant. All right, even though it might be non-significant. All right. So what about this covariate? We know that a continuous variable and a dependent variable are correlated. All right, so we know, let's say, I'm going to use Blake's stuff. He had a lot of fish. We know that length of the fish is correlated to parasite intensities. All right, bigger fish have higher energy demands. They're going to be eating more food. They expose themselves to more parasites. We know that relationship exists. All right, but we don't really care about the significance. We don't care to say it's significant because we already know it exists. It's uninteresting. However, perhaps we're really interested in sex differences, difference in intensities between male and females. Well, if we look at our fish, these fish are often dioecious, where one sex is larger than the other sex. Well, you've just introduced another factor. You said larger fish have more parasites. Well, if one sex is larger than the other, then we already know that that sex should have more parasites. So what's causing this increase, this difference in intensity? Is it actually the length of the fish? Or is there some sort of sex differences between the behavior of the female fish and the behavior of the male fish? So what we do is we create our model and we make sure that that covariate, that length is entered in first and remains in our model so that we can better understand, is there an effective sex or not? All right? So here's an example, kind of what I was just talking about. We're interested in parasite intensity, we're interested in differences in the sex, and we know that our, let's say, female fish are larger than the male fish. So the question is sex important? Looking at this graph, we would say yes. But after going through this class, you'll say, hold on, we've got this covariate thing. We need to look at it. So I make my model. I don't include an interaction because I don't care about the interaction. I just want to account for the size of the fish before looking at the sex. And after we account for size, this is an ANCOVA. This would be a type 1 table. Type 2 gives the same results. But after we account for size, there's no difference in the intensity between the sexes. So even though our graph makes it seem like female fish have a higher intensity, that relationship is entirely due to differences in size and not an inherent difference between the sexes of the fish. All right. One way that we can look at this is after we make our model, there's a function called effect. What that'll give us is the effect size the effect size of that variable of interest in a model that we created. So our model here includes size as a covariate, and then we're interested in the effective sex. And after we account for sex, our average intensity for females is 55.3. Average intensity of males, 54.9. That's not a significant difference. Not a significant difference at all. Hold on. I have my camera covering that up. All right. All right, so why does this work? Well, you have to go back to what the ANCOVA tables do. The ANOVA tables tries to partition the amount of variation between that's explained and that variation that's unexplained. All right. The portion that is explained is all of our treatment variables, all of our independent variables. The unexplained portion is our error. All right. And we already said that the sum of our treatments and the errors equal our total. And then we use F to determine the significance. Well, this F is the treatment. So as we've already seen, when we have multiple independent variables, we can calculate an F for each of the variables to see if each of the variables' explained variation is significantly different from 0. Well, a covariant could be accounting for some of the unexplained variation. So what we can do is include it as not necessarily as part of the treatment, but as its own covariate term. So we now have a sum of squares of the covariate, sum of the squares treatment, and a sum of the squares error. What that covariate does is taking that variation that's in the error term and separating it out and saying this is the amount that our covariate contributes. Do we really care if it's significant? Not really. Now, I do say it's convention to list these covariates first, but if you use an ANOVA type 2 table, so the capital A from the car package, it's going to be default. It's less important as to what order you include it in. It's just much more important that it is there in the model. So we're going to actually look at this. So this is what I was saying. So we take some of that error and we make it part of the covariate. All right, and this allows us to really investigate that actual relationship between the dependent and independent variables. We could, I don't think we're necessarily going to do this, but this is part of our, I'm going to leave this up here so you can read it. We could use a sequential table where we add our terms in order. So we could say, I want this entering in first, and I want this entering in second, and then we look at our ANOVA tables, but it's so easy to make the type 2 tables that I just do that by default. Definitely, if you're doing a covariate, ANCOVA, you can come talk. All right, so what we're going to do is kind of look at this, how to do it. And what we're going to do is use the cabbages data set that's in the mass package. So this is built in. So you can either load the mass package, or, so once you load the mass package, then cabbages becomes accessible, or you can do this, data, and then cabbages, comma, package equals mass. And that gives us access to the cabbages package without actually loading the mass package. All right, so just as a review, we've kind of worked with this data set. I believe we worked with this data set here. And I believe I used it for in undergrad stats too. But this was measuring the head weight of cabbages, right? They have, did we do head weight? No, we did vitamin C. Vitamin C concentration, we had different planting dates and we had different cultivars, right? Well, there was a covariate that was measured, and that was head weight, all right? And we didn't really include head weight. We ignored that. So now let's actually include it. So if we look at head weight and we look at vitamin C levels, what we see is this interesting negative correlation. All right, so graphically it looks like as head weight increases, our vitamin C levels decrease. What's the Pearson's correlation of that relationship? What'd you get? Let me load it in. What's Pearson's correlation? calculate for the Pearson's correlation? Error message? What? What's your error message?
Telling the X must be compared.
Did you use?
I used the wrong function. I'm working on it.
And by the way, I just released the correlations homework.
Homework?
Yeah, for correlations, gives you practice on the correlations.
What's that do?
I don't know, I didn't think of it yet. I know the test is coming up. All right, what's your Pearson's correlation? Did it work? What's that? You got a negative number? How many people got a negative number? What did you get? Did you use Pearson's?
Oh, is that the p-value?
Oh, no. Yeah, that's a p-value. Correlation. Correlation coefficient.
Oh yeah, I got a negative number.
Should it be a negative number?
No, it's got that coefficient, right?
Well, yeah, it should be.
Yeah, it should be. If one increases, the other decreases. Right? If it's a positive correlation, they're both going to increase together. Or they're both going to decrease together. In this case, this is a negative correlation. As we increase our head weight, we're going to cause a decrease in the vitamin C. Now, we don't know if this is cause and effect. We don't know if larger head weights are causing a lower vitamin C. We don't know that. But it could affect, that relationship could affect our conclusion to whether cultivar and date has an effect on vitamin C. All right? So, run our analysis. Let's add in head weight now and see if cultivar and date remain significant after we account for our head weight. So what I'm basically saying, make your model simple, find the simplest model. But remember, well, no, let's just do that. Let's work through it. Find your simplest model. And again, nothing changes. We've already learned how to do everything. We'll assume all our assumptions are met. We'll make it easy. Did you get it? Still working. What's that? All right. So still work. Find your simplified model and then go back. I don't know when we talked about this. Interact two-way ANCOVA maybe. But I'm curious to see what our simplest model was before. Finish up. I'll be right back.
No, I forgot that.
Well, this week, 7 got this slide. You know, I can't understand what he's saying because I'm trying to process the picture. What I mean, listen, right? I'm right on. Well, maybe if you were better. Trying to get better at it, man. Have some respect.
Too dark, chasing much light.
I thought this signified doing on crowd. There's no winking with it.
So it's like the middle objective pitch.
Yeah, probably.
All right, you get it?
Are we doing this wrong? First one wrong?
I just
How are you doing? Okay. Okay.
Sounds like
Do you have significant interactions?
Are we supposed to include headweight on this model?
Yes.
Well, I didn't believe it. How did you do it?
I think so. I didn't hear, but that, oh, yeah, so we don't have to go back. But we're interested in this. We'll talk about it.
Now it works.
So, only cultivar and headweight, right? Just based on the p-values from that first.
Yes, it is.
ANCOVA, right? You have to remove,
You gotta remove them, usually when you remove them, the two values go up, so.
I understand, but.
yeah.
I know what is happening here.
But eventually.
I actually don't know if they will go down. After removal.
So that's, I kind of help you through this. So, if we put together a flow diagram, and anytime you kind of think about stuff, this is something I would probably recommend doing when you have your dependent variable and you're looking at all these measurements that you're doing. Put together a diagram, think about how things might be related. So in this data set, the Cabbage's data set, we ignored the effective head weight initially. So we just looked at date, cultivar, and vitamin C, and we may have had an interaction effect. So we did. We checked for the interaction effect first. All right, and we simplify our model, and if we did it just like this, date times cultivar, yeah, that interaction effect is not significant. We drop it from our model, all right, and it ends up being just the main effects, just date and cultivar. But we also measured head weight. So now we're interested in this possibility that it's not just cultivar and date having the effect on vitamin C, but each of these may be affecting our head weight, which we know then has a negative effect on our vitamin C. So maybe the cultivars themselves, one cultivar is bigger than the other. Well, that affects our overall final dependent variable, or the variable of interest. All right, so what we need to do is try to include this in the model to see, okay, what's the actual relationship? How do we interpret this? So what I did here, let me do this. So I put together, let's copy that, the full model. And I put head weight plus cultivar times date. All right, now I use the plus here because I'm assuming head weight is a covariate. All right, that we know this relationship exists between head weight and vitamin C, and I'm really not interested in if this is significant or not. I'm not going to interpret it in any way. It's just larger cabbages have less vitamin C. What I'm interested in are this cultivar and date. So I make my model, all right, I look at the ANCOVA table, and I see that this interaction is not significant. All right, so I go through and update my model by removing it, and then I generate my ANCOVA table, and this is what I get. All right, again, we see that cultivar is significant, so that's our p-value after we account for head weight and our date. We can see that date is significant, and this is the p-value after we account for head weight and cultivar. Now, in this case, head weight, this is kind of meaningless to us. We don't really even need to report it because we're using it as a covariate. We know that they're related. We want to remove this effect before we looked at cultivar and date. If we were interested in that effect of head weight, I can use my lowercase ANCOVA. And what this does is generates a sequential ANCOVA table. And it's going to enter the terms in the table in the order that they appear in our model. So in this case, head weight appears first. So just looking at vitamin C and head weight, yes, there is a significant effect of that correlation. We know that. All right. Date, we get our same p-value because that's the p-value after we account for everything else in our model. But cultivar gives us a different p-value. If we wanted to get the true p-value, we have to account for date and then look at the effect of cultivar. And we can do that by making a new model. So head weight plus date plus cult. Date of cabbages. Where we change the order, and now you can see that cultivar enters in last in the model. This is the p-value after we account for everything else. Now you'll notice, I'm going to run these this whole entire chunk one by one, so we can look at them one on top of the other. These two are sequential tables, right? Type 1 tables. Cultivar had a p-value 6.967 e to the negative 7. That was when it was entered second. When it's entered third, it's 1.745 e to the negative 07. Date, when it's entered last, it's 0.03. When it's entered second, it's only 0.258. So the only way date becomes significant is after we remove the effect of cultivar. So there's something, something there. We've got our diagrams, our interactions that are happening. Do we have to go through all this? Nope. This is our type 2 table. 0.30526. 0.30526. This value, 1.745, is this value, 1.745. Difference is head weight, which gives us a different p-value. But we don't need it because we're using head weight as a covariate. Now, what if you do it another way? The other way is to include head weight in the interaction term and then work through the simplest model. Well, at this point, this is no longer an analysis of covariance. Now, we would do this if we're actually interested in that relationship. Maybe we don't have any presumption that head weight is going to affect vitamin C. So we're curious, does head weight affect vitamin C? Does cultivar, does date affect vitamin C? Now we go through this model. So we start with the full model, we look at our ANCOVA table. Well, we're going to have to update this. we're going to have to remove it. And we just do everything that we've done, or that we've done up to this point. So we're going to update mod.full. We're going to subtract our terms. Mod 1. Hold on, I got to rerun that. There it is. That's better. So then we go to our next term, which is the next highest p-value. We're going to go mod 2, update mod 1, and look at our ANCOVA table. Go to our next term, that's p-value. I'm going to say ... As we remove everything, we will get to this table as a mod main, and now we can report all of our p-values to say weight affects our vitamin C levels, or head weight affects vitamin C levels, cultivar affects vitamin C level, and date affects vitamin C level. So the difference between analyzing this head weight as a covariate versus an actual effect, predictor variable, comes down to how do you start with our model? Do we keep it isolated and then have plus all of the other terms? Or do we include it as part of the interaction term? That's really the only difference that we have for our covariates. All right, and this kind of lays through that as what Cody mentioned. Our sum of squares will change. They change as we remove terms, as we account for different terms. So I already kind of went through all this on how to do everything. So what do we discover? Head weight, it's an important term, it's an important covariate, probably an important predictor as well. And cultivar and date are both significant. All right. So how do we interpret then? Well, we have our simplest model. So our simplest model will be this mod 1. Let's make this. No, mod main. Mod main is our simplest model. So now we look at our mod main. So we've got a couple different things. One, we know cultivar has an effect. So we can look at our box plots, we can look at the averages, weight of the vitamin C levels for the cultivars and conclude, okay, we can state whichever one is higher has higher vitamin C levels. All right, for date, we can run a post hoc test on that. All right, we can run a post hoc test, and that could be as simple as, since it's just main effect and our assumptions are met, Tukey, HSD, AOV of our simplified model. And we look at the Tukeys. How do we analyze head weight? Now we go to our summary table. Head weight is a continuous term, continuous variable. We know head weight is significant. What we want to now interpret is, well, what's its effect? And this tells us the effect. This tells us the slope of our line, slope of our best fit line for each of our variables. So this is actually this is overall. So as our head weight increases 1 unit, whatever our unit was, we're going to cause a decrease of 4.4 units in our vitamin C levels. Again, whatever that unit is. That explains the relationship. In some cases, we just want to make our plot. Vitamin C is a function of head weight. All right, maybe you color code these for different cultivars and dates and so forth. Maybe you do a different line, best fit line for each of them. I mean, it's kind of up to you, but you have this relationship. We can say, yes, there is a significant negative correlation, and that correlation has an effect, has a net effect of this. As head weight increases 1 unit, vitamin C levels drop 4.4 units. questions? So our continuous variables, if we're going to analyze it, so here's some graphs. I think I have the plots, different graphs that we can do. All right, shows basically the same type of thing. Even though our best fit lines look a little bit different, we know that there's not a significant interaction term. So the general effect is as we increase our head weight 1 unit, so let's say from 2 to 3, we're getting about a 4 unit decrease, 4.4 unit decrease in vitamin C. All right, could we get even better? Yes, this is where the effects package comes into play. Because now we want to, after we want to account for that covariate, that continuous covariate, to say after we account for it, this is how much of an effect cultivar has. This is how much of an effect date has on our vitamin C levels. So this is another package called the effects package, and the function that we use is effect. All right, so on these computers, they should be installed. So make sure you can get it loaded. We're going to use the mod.main or the simplified model. Seconds. So once you get it loaded, the function is effect. We give it a term, and that's going to be a term that is found in the model. So if you do the ANOVA of the model, whatever that term is in that ANOVA table, that's what we're going to use. And that term's going to have to be in quotation marks. It's going to have to be in quotation marks because it's telling the effects function, hey, find this term in the model and report the adjusted mean. The adjusted mean is the average after we account for the continuous variables in our model. I have here after accounting for the covariate because our head weight could be was the covariate. But if you have multiple continuous variables that are significant, this is going to give us the average effect of our categorical variable after we account for those. All right, so here's the effect here, just to kind of show you the difference. I use the aggregate function to calculate the mean of vitamin C levels. This is just a raw, we ignored the effect of everything else. If we use the effects package and look at the adjusted means, cultivar 39 has a mean vitamin C level of 52.88. Cultivar 52 has a mean vitamin C level of 63. Has a little bit, I mean, you still have a difference. These are still significantly different. But it's enough for us to say, yeah, after we account for our covariate, cultivar 52 causes an increase of about 10 vitamin C units on average. What about date? Again, I made the aggregate, or I used the aggregate function to look at the means. Here's our adjusted means. Here's our adjusted means. So 56.4 for day 16. Actually, day 16 went up a little bit. Day 20, 54 up to 55.7. Day 21 went from 63 down to 61. So the question I have, are these values different? Is 56, 55, and 61, are they significantly different from each other? We know a difference exists, right? How do we find out which ones are different? Yeah, I've got the summary, the GLHT, but 2 keys can work. Oh, this is actually, yeah. Now the appropriate one is to use the GLHT. So I think what we're going to probably do is stop here so that we can kind of reintroduce the general linear hypothesis, the multi-comp package again, is simplified. So just as you can see, Tukey's gives a different value. The multi-comp package accounts for those covariates now and uses these adjusted means instead of the raw means. So, all right, so we'll stop here. No class on Monday. Make sure you go support the rest of the grad students. Then on Wednesday, we will kind of pick up, reintroduce the multi-comp package again, since we're going to need it with the covariates. And don't forget the exam. I'll send out reminders for the exams. But that exam will go live tomorrow morning, I don't know, 4:30 in the morning. 4 questions. Don't wait until Wednesday afternoon to start it. I was going to include this. Let me exit out of here. As I was doing the homework, you guys probably did this. I had restricted permutational ANCOVAs. And I don't have anything here. All right, so there's that option that cache equals t that you can put up here. I thought that when I run this chunk, it's going to cache it. The answer is that when you knit it, it's a whole lot faster. Not really how it works. I found that out the hard way. But if you use it and you knit it and then you realize, oh crap, I forgot to put my name on here, all right, and you fix it and then reknit it, then in theory, all of the cache files should be there. So then you don't have to wait for it to redo all of the randomization stuff. I was really hoping that when I use that cache and I get a p-value, I write the p-value down and the p-value stays the same because we cache it. No, it apparently only keeps the cache when you knit the document. But it could be useful if you have to remake it. All right? All right. It's going to be it for tonight. Multi-comp package next. And we got to get that flight.csv.